Hi, everybody. Thank you so much for joining IFMA's webinar series. Today, our webinar is focusing on climate smart renovation, understanding the impacts of phase change material or PCMs ceilings. So these materials are emerging as a powerful solution for improving energy efficiency. And our panelists today are going to be taking a look at that and exploring it with us. Uh, Please, before we get started, let us know where you're joining us from. So my name is Kim Jackson, and I'm joining you from Houston, Texas. In that same place in chat, please also share any questions or comments that you have as you're watching the presentation so that our panelists will see it and they'll be able to answer any questions you have. Unfortunately, our FM that was on the panel is FMing due to ongoing issues related to a power outage over the weekend. Ian is unable to be on today's webinar so that he can work with a contractor to get this issue resolved. But without further ado, I'm really interested to see how we're going to be able to integrate this for a climate smart renovation. So I will welcome to the screen Mick Dunn. If you would please join me and go ahead and get us started on our webinar today. Thank you.
Thanks, Kim. Nice to meet everybody. My name is Mick Dunn. I'm from Armstrong World Industries. We are in Pennsylvania. Lancaster, Pennsylvania is our headquarters, and well known throughout the industry as a manufacturer of ceiling tiles, a 160-year-old company, publicly traded, and really excited to explore and sort of share some of the more recent advances of different types of technologies being integrated into ceilings in general, and some of the results and effectiveness of what we see within that. And so joining me on today's presentation also is Nathan from IES, and so he'll take us through some of the information regarding what we're learning about things like energy modeling and how this type of technology we'll share can be useful in buildings to help address a range of different things, from thermal comfort to HVAC load and controls opportunities. So we're going to be exploring what we're talking about here with this idea of PCMs and how that enhances building efficiency and operations. We'll evaluate and consider how these technologies can get integrated into ceiling systems. We're going to assess some of the operational benefits of doing PCM retrofits, and then apply that with both simulation tools and some field study examples of how we've seen this play out in a range of different applications. So to kick things off, one of the things that we tend to think about when we think about ancient buildings, the earliest dawns of civilization across the world, when we see these structures that have been lived in and used, often we're seeing very sort of earth-based, mud, clay, other types of material structures used to create shelter. And over time, this sort of evolves and grows. And even in our older buildings in our cities like Boston and New York, and even our local cities, many of our museums, our city halls, our cathedrals are very thermally massive, a lot of brick and a lot of granite and stone and these types of materials. And so traditionally, not only was these materials used to create structures and shelter, but they were also used to help control temperature in buildings. So thermal mass up until the early 1900s is really the predominant way that we would control heating and cooling of structures for comfort. And so it's not until the advent of both insulation and more modern cooling mechanisms that we see a change to the way that we build structures, and in particular insulation. So as we move into the early 1900s, we see a rapid transition into lighter weight construction methodologies. It's not uncommon in a global marketplace to be able to manufacture a wall system in another country even, or another climate or area of the US, and ship it and transport it to a job site for fast and easy prefabrication, so to speak. But we see a lot more glazing. We see a lot more metal and other composite materials windows and things like that that give us faster construction times, lighter weight structures so that we need less and less sort of supporting structure and such, gives us much better views and sometimes more bright lights and things like that. All of these are great things that we have in buildings, but over time we've been slowly stripping thermal mass away from buildings. And that's what we're sort of exploring today, is the role of thermal mass. So we could think of thermal mass a little bit like an energy storage mechanism, right? When we talk about energy storage, we tend to mostly be focused on electric storage, battery storage, lithium-ion batteries, either in cars or connected to solar farms and other grid utility systems. But another type of thermal storage is thermal mass. And so we can literally charge up a room or a structure that's got a lot of thermal mass, say with heat, and have it hold that heat, or vice versa. There's different types of thermal mass that we might think about. Some of those are things like concrete and brick, and more traditional types of thermal mass. Another type of thermal mass is water, which we have in our hot water heaters. And so we heat up our hot water heaters so that we can respond to a large fluctuation in demand later on, and we're literally storing thermal energy. Well, another form of thermal mass, or a form of thermal energy storage, is what's called phase change material. And so anytime a material is undergoing a transition from a solid to a liquid, or a liquid to a gas, it's undergoing a phase change. And the most common type of phase change material is ice or water. So when ice is in an environment, say taken out of a freezer and exposed to above 32 degrees, it will begin to melt and absorb heat. That's what's actually keeping the cooler at 32 degrees, is the ice undergoing a phase change. And it's not until all of that ice is completely melted and you've essentially got a cooler full of water that it will then begin to increase, albeit more slowly. It will increase in temperature as it's influenced by outside conditions. If you took that same bucket of ice, or water rather, and you exposed it to a freezing cold environment, say take a cup of water, put it in the freezer, it will drop down in temperature until it reaches 32 degrees, and then it will begin to freeze. It will maintain 32 degrees while it's still freezing, and it's not until it's completely frozen that it will then drop down in temperature to match what's in the freezer. So this is what we call a solid to liquid phase change, and it's storing and releasing large amounts of thermal energy. That's why it's both a thermal mass but also a thermal energy storage asset. We use phase change materials every day in our buildings in the form of refrigerants that are really just doing liquid to gas, constantly moving refrigerants throughout our building using compression cycles so that we can leverage that same benefit in all the more efficient HVAC systems. So what would happen if we could take a phase change material that transitions from solid to liquid or to gel at room temperature and use that to help stabilize temperature in buildings? And the result is that you end up having a product that can essentially deliver the type of thermal mass we expect from things like concrete and brick, without the huge embodied carbon challenges that come with deploying traditional thermal mass into buildings, so that we can still have some of that stability without some of those penalties on the sustainability side of things. And so Armstrong has released and used some phase change material in what's called our TempLock line of ceilings, where it's added to conventional ceiling tiles, almost like a backer that is helping stabilize temperatures in buildings and helping support climate and comfort goals. So this is helping contribute to reducing thermal loads in buildings. So it can be used, which we're going to explore later on in the presentation, to help support difficult to maintain spaces that can't reach set point, or perhaps just to help stabilize as critical backup in spaces, to optimize HVAC operations, and most of all, improving occupant comfort. And so there's different things we can also do within the HVAC programming, very simple things to say purge a space overnight or early in the morning with ventilation, and other things we can do to set back and just help leverage the benefit of these phase change materials. But what we're talking about when we talk about this thermal energy storage is on the average about 50 BTUs per square foot of thermal energy storage being added into a space. If you imagine a typical classroom, adding, say, 600 square feet or so of phase change material, it's almost like adding a couple ton hours of HVAC storage battery capacity to support the operation of the building. And so what we're looking at here is on the bottom left is a regular ceiling tile, just like what you would normally see. There's really no change to the look or function of the ceiling, but on the back of that ceiling is a metallized film that is containing this gelled phase change material. And what's in there is actually a mineral formulation, almost like a salt, very similar to salt that you may use on roads and things like that, that is crystallizing and dissolving at that room temperature range to help support that comfort. And one other note that's worth mentioning relative to the way that is deployed in the ceiling, if you look at this image here, which is more of an airport application, you'll see some downlights, sprinkler heads, HVAC devices, perimeter tiles, and things like that. Wherever those things are taking place is a regular ceiling tile, and the phase change backer goes wherever the full tiles are within a space. So it sort of means there's about 50 to 70% coverage of a given space to deploy the thermal mass into the building and provide that comfort. So unlike insulation, where you need 100% coverage and really good air sealing, it's more like the ice in the cooler. You just need enough ice to make a difference, right? And it's a very similar process. So doing this means it's very easy to retrofit it into an existing building just by switching out the full tiles. And it also does not impact labor on new construction and renovation projects because we're installing it as we go, and installing those full tiles means there's really no change to that labor process. And so one other element worth understanding, there's whole other presentations on this kind of topic, but thermal mass as a general umbrella of technology is recognized by the federal government as qualifying for tax credits under what's called the Section 48E Federal Investment Tax Credit. And really all that is over the last 15, 20 years, if you've ever done a solar project or heard about some of the tax credits towards solar, even for homeowners, they'd put solar panels on their roof, they'd get up to, say, a 30, 40% tax credit from the federal government. This was expanded to include more technologies over the last couple of years. And even with the most recent Big Beautiful Bill, those changes, even though are going to begin to sunset some of the technologies like solar, there's technologies like energy storage that have been baked in currently until 2032, and phase change material is a qualifying thermal energy storage technology.
Talking up to 50% in tax credits, this energy-saving ceiling can actually cost less than a traditional ceiling installation. TempLock harnesses the power of phase change material to passively store and release heat, lowering energy usage. This thermal energy storage technology now qualifies for tax credits for all eligible U.S. taxpayers. Both private and public entities qualify. How do you qualify for up to 50% in tax credits? The incentive begins with a base tax credit of 6%. 2% is automatically added because TempLock meets the Made in America content requirements. A 5x multiplier is added if the project meets prevailing wage requirements or is less than 1 megawatt hour of energy storage. The overwhelming majority of acoustical ceiling installations are well below the 1 megawatt per hour of energy storage threshold and qualify for the 40% credit. An additional 10% is awarded if the project is located in the energy community. Energy communities have been historically dependent on fossil fuels and disproportionately burdened by pollution and legislation. Like all of the credits, the additional 10% credit not only covers the ceiling panels, it also includes the accompanying grid, trim, and labor. So let's see how this breaks down in a 100,000 square foot acoustical ceiling project. TempLock ceiling tiles cannot be cut, so standard coordinating tiles will be used for the borders and cutting needs. In our example, traditional acoustical tiles cost $100,000. TempLock energy-saving ceiling tiles cost $200,000. The grid and perimeter trim equal $350,000, and the installation labor adds an additional $250,000. That's a grand total of $900,000. Apply a 50% investment tax credit to the temp block ceiling tiles and accompanying grid and perimeter trim and labor, and the cost nets out at $500,000. That's a $400,000 savings with temp block, exclusively from Armstrong.
Hopefully that little video made sense on the tax credit. Sorry, that jumped in really quickly. I wasn't expecting the video to jump in, but that's intended to just kind of help give a little bit of an overview of how this tax credit works and how that sort of impacts things on the budgeting side. It can really be influential on tenant improvements and new construction projects, helping reduce overall project budgets, leveraging that tax credit, and just bringing those applications to bear on different projects to help out on the budget side as well. And so I'm just going to dive in before we hand over to Nathan on some of the energy modeling type learnings, on just covering some of the applications of like, where is this a good technology? It's easy enough to say with a lot of technologies everywhere, every time, all the time. And although it is useful and beneficial to be adding thermal mass into structures whenever we can, there are certain applications that it's particularly favorable for. So the first one of that we might think of as spaces that can really leverage night ventilation, spaces that get cool enough overnight where we can use especially outdoor air to cool our building if it's summertime, so we can purge the building. So those tend to be climates that are drier at night, especially, and we can leverage that without having to induce cooling. You can still do that in a humid environment, but you're going to be doing that using air conditioning and what we might call COP arbitrage. You're running your cooling system at 4 a.m. in the morning to drop temperature when conditions are favorable so that you can save cooling energy later on, but it's really favorable in some of these night ventilation economizer opportunistic climates. Others are zones within buildings with high thermal loads. So sometimes within a building, top floor of the building, corners of buildings, areas with a lot of solar gain, maybe indoor occupant areas like lots of classrooms and gathering spaces and function rooms tend to be where the biggest loads show up in buildings and can be advantageous for things like phase change material. Inefficient buildings, so buildings with a lot of issues, especially with lightweight structures that don't respond well to large fluctuations in temperature. So you've got a building shell that's like a pre-engineered building that's quite different in terms of its thermal mass to obviously a brick structure or block structure with a good insulation. So these types of things are also where we see a lot of opportunity. And then finally, climates and locations with big differences or opportunities with peak demand and time of use utility rates. So whenever we go into areas where there's a large difference of cost of energy in the afternoon versus the morning, or in the summer versus the winter, tend to be other areas where it's more financially advantageous to explore the technology as well. And so then finally, when we think about what kind of buildings are good matches, often we're thinking about buildings that are predictably occupied. They're most often occupied during the daytime, empty at night. They could have variable occupancy throughout the day. But the key is that there's the opportunity to shut the building not down, but do setbacks and leverage things like purging of cooling early in the morning without creating occupant discomfort. So if we were to think of areas that are occupied 24/7, these might be areas where we're going to drive the least amount of benefit on the thermal mass side. So you could think about an operating room in a hospital or patient room or multifamily housing. It's much more difficult to manipulate thermostat to get additional benefit if the goal is to be supporting HVAC and to reduce energy usage. It is still, however, beneficial in some of those applications as more of a resilience critical backup as power outages and other issues happen, or particular concern around meeting set point. We're still able to help with some of those things, but areas that are predictably occupied and have periods of vacancy give greater opportunity to leverage the benefit of the PCM. So in the summertime, the way that shows up is typically speaking, a building without thermal mass, in this case without PCM, will see a bit of a wider temperature swing. And so the lows are a little lower and the highs are a little higher. And that's kind of what we see in the dashed line there, compared to, say, a room that has, or a building with more thermal mass will shrink that delta T a little bit more. And so the result is, in the afternoon hours, if we can shrink temperature and push the peak out of that temperature a little further into the afternoon, we're generally saving energy at the peak of the afternoon, hopefully when peak demand and energy consumption costs are probably at their greatest. And then overnight, we're releasing that, hopefully with fan energy, sometimes with more efficient cooling, and recharging the ceiling for the next day. So that may simply just mean having a set point of, say, 70 to 72 degrees early in the morning, favoring economizer cooling, and then setting that up so that we can then absorb that later in the day. And we'll see that in some of the case study information that I'll share later on. On the wintertime, it's almost like the exact same chart, but the benefit happens in reverse. We're absorbing heat during the day, which is particularly favorable in buildings where there's high internal loading. So we've got a lot of students in the room in a school. We've got a lot of solar gain in high-rise buildings, say in New York, and even in cold climates. We have a lot more free heat flowing around in a building than there ever is free cooling. So we can harvest some of that heat, store it, and give it back later on. And that later on tends to be overnight. We tend to be releasing our heat back into the space as you set the building back and it empties. The PCM in the ceiling is refreezing and releasing heat and stabilizing temperatures as it rejects its heat back to the space at 70 to 74 degrees overnight. So we're going to hand over to Nathan on this next section, as I just kind of give you a quick idea of what we've been doing and how we've involved a partnership with IES on the energy modeling side of things. A big sort of gap in the market sort of existed when Armstrong began looking at this technology to help support projects. But the first step of that was validating the technology itself. There's sort of like benchtop testing you can do with phase change materials to measure their heat capacity, things like that with ASTM standards. So we can measure the amount of storage capacity we have. But then the next step to that is like, well, can we see that show up in a room in calibrated sort of larger room testing data, which is what we were doing sort of as the next stage in early development, to see the influence of phase change material being added in and being able to measure that both in the ceiling and HVAC operations in very controlled environments. And then moving that into the field and doing sort of detailed field studies that would go into measurement of energy and temperature, and being able to calibrate that back, in this case with an energy model that can kind of simulate and match the results of what we're seeing in those various stages of development. And so that's been the kind of pathway we've followed over the last year in a partnership with IES. And I'll hand it over to Nathan to take us through some of what we've been learning on that. So Nathan.
Thanks, Mick. Appreciate that. I'm going to have everyone mute yourself while I'm talking there, Mick. Mm-hmm. So thanks, everyone. Appreciate the introduction, Mick. As Mick said, we've been working in the last year or so with Armstrong to improve and develop methods for applying phase change materials in the energy modeling workflow process, and how that kind of corresponds to folks like yourselves who are maybe looking at ways to save energy or decarbonize buildings. Energy modeling can sometimes seem overwhelming. And one of the things in particular with phase change is the physics of, it sounds really elegant to talk about, and it changes states between liquid and solid. And the reality is the physics of that is very complex. I won't bore you all with the very technical, very nerdy deep dive on all of that, but suffice it to say, through a lot of research, a lot of work, the phase change itself, the physics is accurately captured while maintaining the usability. So it doesn't take a lot of time. It used to a year or so ago. I mean, I've been doing energy modeling and working with phase change for several years just on the practitioner side of things, and definitely getting accurate results of the phase change. The time it took to validate that the models that you were building oftentimes from scratch were working was a huge undertaking. So all of that is to suggest we're going to talk about operational cost savings, thermal comfort and performance verification, the integration of the BMS, sustainability, and capital and risk reduction. And go ahead there, Mick. So firstly, the operational cost savings. So in addition to obviously tax credits, you can also reduce your energy bills pretty significantly. So I'm going to talk about a simple, relatively simple building that we've studied here to start to point to some of the direction. And the advantage of doing energy modeling early on is it can also facilitate looking at multiple buildings, not just a single location or a single building. As I'm sure many of you know, every building is unique. Every building's got its different challenges and opportunities. And one of those things beyond the looking at it in sort of conceptual bit is to also then translate that over to performance verification. So with the models and with the advent of digital twins, although that term is probably used too much, we can also validate that what we're doing in the models is now working in the real world, or if it's not, identify why not and then fix it rapidly. So thermal comfort studies, as Mick pointed out, can be done as a part of the simulation work. Just to show that added benefit prior to making the large capital expenditure. Go ahead, Mick. So in this example here, we have a typical, let's call it a code minimum compliant building, or something that is sort of the minimum building that could be built at the time of construction. And that EUI, or energy use intensity, might be 45 kBtu per square foot. Adding in 70% ceiling tile coverage with phase change can result in a reduction in that EUI of about 7%, 6.7%, conveniently 6.7 for those of you with kids. And then we can get into the iteration number 2, where we then tie that back to leverage that PCM, or that thermal mass, even further, going and tying it into making some no-cost changes to the BMS system, or the HVAC controls. Then we can get that savings to nearly 12%. So this corresponds very closely with the total energy cost reduction as well. Go ahead, Nick. In addition to that, a lot of organizations and municipalities have also added on sustainability requirements. For example, New York has Local Law 97, where they are going to penalize people for failing to perform. There's 179D tax credits, which focus on the operational portions of this. And adding thermal mass to these buildings is one of the strategies that, when tied with other complementary strategies, can really squeeze the most performance out of the building and hit those decarbonization targets or goals. Go ahead. And capital planning and risk buildings, in addition to those sort of market drivers from the sort of the governance side, there's been some surveys conducted recently that a lot of folks are planning on being in more environmentally friendly buildings. So 36% of businesses plan to leave inefficient properties, and 43% will increase their focus on embedding the net zero carbon requirements into their new locations. So this is definitely front of mind. And then leveraging phase change, as I mentioned, with other technologies. So the bottom image there is a lot of permutations that are run, things like changing to LED lights, for example, making changes to HVAC controls. How do they correlate, and what's sort of the optimal path to leverage phase change and other strategies to get the carbon or the energy or the cost as low as possible? So simulation gets leveraged in a lot of those early stage planning. I mentioned that case study of sample office building. Going a little bit deeper on that one, that project is in Denver, Colorado. We did do a good job on the lighting power reduction. So the code maximum is like 0.87 watts a square foot. So this one's at 0.6. And then taking a look at internal gains and reducing those. So standard 90.1, IECC, Title 24, all of the codes and standards are really focused on load reduction. In addition to envelope optimization, which starts to get to the point where, well, we've done almost everything that we can on those fronts. And now what other opportunities are there? So controls, phase change, looking at the interior assemblies really starts to bubble up as the next big opportunity in taking your decarbonization or energy cost reductions even further. So go ahead, Mick. So coming back to this, we've integrated this back in here so we can get just a demonstration here of the importance of not just thinking about any one technology or any one product as a quote unquote silver bullet, but identifying products or technologies that can leverage other existing technologies, in this case HVAC controls, to get more above and beyond just the sort of standalone entity. So building systems are complex and integrated, and energy modeling helps unpack that. The other side of that as well, as you'll see as we advance through these slides, is sometimes you have, and Mick kind of touched on this, you may see an increase in fan energy at the offset of a decrease in your natural gas bill, for example. And that's normal as long as, and the idea here is to show that the net is headed in the right direction. So this is that base case breakdown. You can see here the heating and cooling numbers and the fan energy, heat rejection, which is the outside fans in this case. But we can see that that energy is at a given level. If you go to the next slide, you see that the heating electricity goes down, the cooling electricity, the fans start to creep up. And if we get to the last one, you'll see that the heating continues to go down, the fans come up slightly. So the strategy here was to expand the operation of the fan, to let the phase change, to leverage that phase change more, move more air across that phase change so we can get better heat transfer. And that's a much more energy efficient strategy than running the boiler or the air conditioner. So the models are validating the case studies, and the case studies are validating the models. And what we're able to then demonstrate is do this on any particular project before you make the capital investment, to help guide and understand all of the opportunities for whether it be rebates from utility companies, tax incentives, or just straight operational reductions. Thanks, Mick. Oh, I forgot I have a little bit more detail on this because I'm a nerd. So we have a little bit more going and comparing the ACT. This is looking at the temperature, or the load on the heating coil. So the green line is the regular ceiling tile, and the red line is what happens to the load on the coil when phase change is applied. So you can see a general reduction in shift. And if we then move to the next slide, this is where we adjust the controls to leverage that phase change or that thermal mass even further. So the purple line now says, okay, we've got a benefit. Let's take that benefit and extend it. And then you can see the reduction in the peak load is even more pronounced and shifted slightly as well. And I think that's my last slide. Yes, it is. Mick, you're on mute.
Thank you. Yeah, I muted myself so I didn't pollute your. So the LA.
Your audio is really quiet.
Okay. Is this any better? I'm sorry.
Getting a little better.
Okay, let's see how this improves, but jump in if you're finding that it's difficult to hear me. But this is also a model. We're going to transition from here into some real world case studies. But this is also a model in a fairly moderate climate on a coastal area in LA. Looking at medium-sized office building. And so here we're looking at some of the results and, what we're seeing in some of those moderate climates for opportunities. And what you're looking at on the bottom right of screen is sort of like a quick visual representation of what happens within the energy modeling software. There's some drop-down menus for people that are in the energy modeling space. It's a fairly simple, straightforward process. If there's an active project already using a model to introduce this into the stream of the project. But we can still learn a lot about how to run our buildings from what the modeling information is telling us and use that. So here we can see some of the differences in monthly energy usage on the cooling side. What you can notice is some of those savings are a little bit more pronounced in the shoulder seasons, which is also what we see. So once we hit that sort of, May and June periods and the September's, October's, the percentage of difference is a little bit larger, and that's often because it gets a little cooler at night in those periods of year. So it might be in some climates more difficult to bring in ventilation for your cooling strategy in the middle of August. So even in LA, we're able to do that. But perhaps if we relocate the building into an area that's a little bit more strenuous, like Palm Springs, which is inland California in a desert climate, it's not getting cool enough to simply use ventilation. And so perhaps our energy savings might be more pronounced, again, in more of those shoulder seasons where we're getting natural benefit, but it doesn't mean we still can't drive energy savings in the peak of the year as well. The bottom of this is just kind of showing the difference in the peak cooling profile on a typical warm day in July. So you can see with the PCM ceiling, the cooling system turns on a little bit later in the morning. That the building is already cooled itself down enough and feels comfortable enough. And then as it turns on and coasts throughout the day, it's essentially using incrementally less cooling to meet set point. And this is really not as much focused on the control side of things, but just simply introducing the PCM and sort of seeing what the modeling is telling us what the difference is. And so on the heating side, we see a lot of the same things, but it's much more pronounced in terms of the heating reductions month by month. This is because in an area like LA, it's already fairly moderate, fairly low degree days of heating to begin with, and lots of free heat available during the daytime. So there's opportunities to store that heat and give it back later on. So a lot of the heating is happening for early morning warm up. And that's where we can be helping reduce energy. But at the same time, what we know is that from the model is telling us that, for example, on the top left here, we're seeing a profile of a typical February day on the second floor of the building on the south side, where we're getting a lot more sun gain. And you can see that the green line is showing us a large fluctuation in temperature. This is not with the phase change material in there. It's really just showing us an opportunity where there's a large difference in temperature happening as a result of large solar gains. So during the daytime, even in February, it's showing temperatures getting close to the mid 80s on that second floor to the south. So there's areas within a building that the technology can be particularly suited to in a myriad of different climates when we think about areas that have some of those issues with, higher solar gain, a lot more occupancy. In this case, it's indicating that there's a simultaneous heating and cooling event going on in these typical winter days at that part of the building. And that's what we're seeing in the bottom right. There's a morning warm up. And once the morning warm up's done, the sun's up and it's kicking in, and we transition to needing to do cooling. Even though that cooling could be economizer cooling, if you're lucky, it's still two things happening at once in the same 24-hour period. And these are target-rich opportunities for the use of something like phase change material when we see that happening. I've even been through buildings in New York City in the middle of January, high-rise, and they're cooling the building during the daytime and heating it at night. So these are the types of applications that thermal mass can be particularly beneficial for. And so the general results of this project was about a 7% reduction in cooling, a 30% reduction on the heating side, and then about a 13% reduction on the fan energy side. So certainly if we began to modify and stretch out those results using controls, which is what Nathan was showing earlier, we would expect those fan energy savings to come down because we'll use a little more fan energy in the interest of making that, for example, cooling energy boost up a little bit further. But here we're seeing an EUI reduction of about 1.75 kBTUs per square foot. So a meaningful indicator that this is something that can be helped to use anything from meeting things like LEED credits, but also satisfying various code requirements for energy code goals. So finally, we're going to jump into some example case studies that I can take you through. The first one is to share what Ian, the facility manager, would have been sharing with you today, which is a case study that was done on campus at Armstrong to help validate and test out some of our assumptions and theories around how best to operate buildings and see if we can see that show up on more sort of sophisticated, complicated buildings. In this case, this is what we call a living lab on campus, a fairly large office area, fairly new construction. It's about a 10,000 square foot office space area that we retrofitted the phase change material with. A lot of different things going on in here, from open office areas, which you can kind of see in the 3D diagram, to conference areas. So there's gathering spaces, small rooms, larger open spaces, and it's fed using a centralized boiler plant and chiller plant. And so a little bit more difficult to do things like measuring of energy in detail because we're sort of not at the mercy of having a single HVAC unit on the roof to be able to monitor energy consumption on. But we can see a lot through observing and monitoring heating coil flow rates and things like that, and differences in temperature and operation strategies. So the building was already a fairly advanced design and construction project that Armstrong had undertaken previously that was really sort of showcasing a lot of the forward-thinking sustainability things that both in our own products, but also everything to do with indoor environmental quality monitoring. So a lot of the spaces are monitoring both air quality and temperature on a constant basis, a very detailed energy management system, and lots of interest in occupant comfort. And so that sort of paved the way for really good baseline data for us to use to then do a retrofit and begin to experiment and see what we could see as a result. So in that process, we installed a section of the building with some temp lock in about August of 2024. And it was quite warm in August. We didn't do any changes to controls, really just put it in, see what happened. And one of those observations was because it was so warm and because the controls weren't necessarily set up at the peak of summer, the phase change material wasn't fully transitioning. We weren't getting strong fluctuation in temperature to drive the full benefit of the PCM. So we could observe in some of our data that there's more we could do. And what would happen if we were to really leverage the controls and institute some of what we were talking about earlier with economizer cooling in this place. So specifically, we ran a series of experiments really focused on the cooling side of the equation of what might happen if we intentionally cool the building down with economizer cooling, and perhaps do that for longer than we might normally do. But we left the building in economizer cooling from 1 a.m. to 5:30 a.m. We wanted to guarantee that the ceiling was no question that it was 100% ready for the day ahead. And typically we had a 70-degree set point at occupancy. And the strategy was to incrementally raise the set point as we neared closer to the afternoon hours. We had a series of sensors installed on the tile to measure energy absorption and release, scattered throughout the building so that we could sort of monitor what was happening and allow us to sort of more fine tune our HVAC operation and sort of test out some of our assumptions. And so the strategy that we employed is on the left. If you were to look at that black line, you'll see that's actually the set point of the space. So like I said earlier, we ran it overnight at 68 degrees and kept that temperature so that we could be really certain that that we were beginning the day with a fully charged ceiling. Before people are coming in to work for the day, we're raising the temperature back up to the 70-degree comfort point. And then once we hit mid to late morning, we're slowly beginning to incrementally increase set point from 71 and then up to 70, sort of 2.5 degrees mid-afternoon, all the way up to 74 degrees late afternoon. And so the idea is we're sort of not turning off our HVAC, but beginning to slowly set back HVAC earlier in the day as the building begins to empty. So typically, if the building were setting back later at night, it might be doing that at 6 or 7 o'clock or 5 o'clock when the building is empty and just shutting off to say 80 degrees. In this case, it's a slow release before that final setback takes place. And so what we saw in the absorption and release, both in the heating coil and the measurement of energy that we're sort of seeing on the tile itself, was a large release of heat happening in the first couple hours of that ventilation. So most of our recharge is happening within about 1 to 2 hours of economizer cooling. Now our ceiling's charged, but we're just making sure through the rest of the evening. And then as temperatures rise throughout the day, which is what we're seeing on the right side there, we're seeing essentially that inflection point happening as the building is occupied and begins to go above 71, 72 degrees. Now the ceiling begins to do its work. Now it begins to absorb energy, and we're concentrating that further in the afternoon, and we're sort of pushing all that energy across the afternoon during the peak hours, where we're assuming is the most expensive and least efficient time of day to be doing cooling. And so the result of that, when we're comparing fairly identical days in terms of weather patterns over 24-hour periods, we saw an on the left side is like a profile of average energy usage over the hours of the day, and we can see those peak hours. On the right side, we see this increase happening on the cooling coil when we're just measuring the cooling coil energy. We're seeing more energy being used in economizer cycle, so that would induce more fan energy, not as much chilled water in chiller energy. So there's an increase there on the coil, and then there's a decrease in the afternoon. So really the idea there is we're reducing chiller energy in that afternoon peak. And in this case, we're seeing up to a 30% reduction in that peak. And that's not to say you put this in and you get a 30% reduction in peak, but it is demonstrating that you can have significant impacts when we set up controls and really stretch that and just try to use that to validate some of our assumptions around, can this technology make a difference? So on the average, however, we're seeing around about 12 BTUs per square foot of area. So it's offsetting about 3 ton hours of mechanical cooling on the average in the area that we had installed it. And so this is our second and sort of final example of a case study, which is in Palm Springs, California. Desert climate, very applicable type of environment for this technology because of a lot of the things that we talked about earlier, but really large cooling demand. And so a perfect application here is side-by-side comparison of portable classrooms. Not only are they lightweight, don't have a lot of thermal mass, but they're very good test cases because they're little microcosms of heating and cooling that can be independently measured and compared. So that's exactly what we did. We measured 10 or 11 modular structures and first confirmed how well they were operating side by side to each other, how close were they, but also just monitoring their energy usage, and then doing a retrofit in about 4 of those classrooms with phase change material. And that gives us the opportunity to compare A/B testing, A versus B classroom in the exact same environments, but we can also take B if it's the phase change and compare it before the phase change was installed and after. So we can compare it in what we call difference in difference analysis. We've got 2 ways we can measure and get greater confidence in some of our results. And so here's sort of a snapshot of average over the course of quite a number of weeks, averaging out the temperature profile of what we're seeing in some of these classrooms. Again, these are significant heat loads that they're under. So we're sort of testing the technology in some of its harshest type conditions. The dashed blue line is showing what the average temperature was just a couple feet or about a foot below the ceiling in some of these classrooms. So this isn't even in the plenum, but just 6 to 12 inches below the ceiling. In the non-PCM classrooms, we're seeing up to a 95-degree temperature. So if you're trying to maintain 74 degrees down below to 75 degrees, what that means is the HVAC system in these classrooms are running round the clock during the day to maintain set point, and set point, or temperature rather, was still continuing to creep. So couldn't keep up. Introduction of the phase changes, these 2 averages on the right there are showing the green and the orange, a reduction in what that peak is and slowing down how long that happens. So 2 things are happening. We're reducing the peak temperature by about 5 degrees, and we're shifting when that peak happens to later in the afternoon. And so when we're looking at the ceiling profile itself, up above the ceiling in that plenum, again, these are portable classrooms exposed with like metal roofing and fiberglass insulation, a lot of thermal bridging, a lot of thermal pressure on those structures. So it's getting up to 100 degrees in the plenum. And then the backside of that ceiling is the green line there. So the backside of the ceiling tile is getting up to 95 degrees in that environment. And below that ceiling, at the ceiling level, that room temperature is exceeding 80 degrees by about 10 or 11 in the morning. And that's what you're seeing at the bottom left of screen there. And it stays above that 80-degree temperature for most of the day, which is making it all the more difficult to maintain 74 degrees at the human comfort level. On the right, what we're seeing is a reduction in all of that, where our ceiling temperature and above ceiling is reducing, but most importantly, that room temperature or the ceiling right below there is not exceeding 80 degrees until about 4 or so, 5 o'clock in the afternoon. And so we're holding that temperature for longer, maintaining some of that comfort. And even though it does still exceed that 80-degree point, it's at a point where the building is no longer occupied. And in this case, the HVAC system has been turned off. So it kind of gives us a sense of how thermal mass can help influence a space. And in this case, we're talking about very light thermal mass, lightweight, highly retrofittable. We're adding about a pound a square foot to a ceiling grid system that doesn't need to be changing your ceiling grid to retrofit this into buildings, and doesn't really need to modify significantly anything to do with the design of new construction and tenant improvements. And so hopefully, that gives you a bit of a summary or a sense of how this could be applied in an array of different buildings, and happy to turn it back over to next steps on questions and such.
There are a couple of questions in the chat, Mick. I don't know if you're finding
Yeah.
them.
I'm sorry, I can't see them, but I'm gonna zero out of my screen share and hopefully I can see those questions now too. Sorry, thank you. Okay, so let's start from the top. We've got a question on, is the indoor temperature range of the testing, how do the specific PCMs work? Is there a specific set per temperature range? So the phase change material itself is designed to transition over sort of a room temperature range of about 70 to 77 degrees is where it's most active. And so most of that energy distribution happens between about 72 and 76 degrees. Once you exceed, say, 77 degrees, it's getting closer to being fully melted. Once you're below 70 degrees, you're closer to being fully frozen. And so that tends to respond to most temperature fluctuations we see in buildings, but in some climates, it might require you to do some cooling early in the morning to get the building down to, say, 72 degrees or so to achieve the freeze that we're looking for. So that would be sort of the goal of recharging the ceiling, is at around about 72 degrees is where that tends to happen. So how much additional was the cost for add-ons for relaying back accurate data, IR temp concerns, controls, relay sensors? How much additional was the cost for it? So in this case, I think, if I'm understanding it correctly, what was the cost of doing some of the add-ons for measurement and verification? Those were projects we were funding under our own M&V efforts. Typically speaking, if you're adding the PCM to a ceiling, it might be adding, say, a couple of dollars a square foot to a project. And the tax credit is what's helping leverage anything to do with the difference of that in terms of netting a potential overall cost favorability. But there's fairly simple technologies that can be used for some of this measurement and verification in terms of temperatures. And if somebody was interested in trying to do that, then we could certainly help with supporting some of the devices and things like that we use that are readily available and fairly low cost. And also, did the census see any other unforeseen factors with setback temps or patterns, depending on the section of your facility focused on? So not so much in terms of unforeseen conditions that we've been seeing. I guess the unforeseen for us in, for example, the Palm Springs study was the assumption that set point was being met and that it turned out that was not the case. So when we did some early studies of the Palm Spring project looking for energy savings, it was very difficult to find it because the HVAC system was just constantly running. So we were going from a position of constantly running to still running all day, but temperature significantly more comfortable, closer to set point. So we've seen some of that in data, and I'd say across looking at many buildings, one thing I can say for sure is nobody sort of knows what's going on above their ceiling. There's a lot of variability in what happens above ceilings that we sometimes forget. We've got heat loss coming from ductwork in the middle of the winter. We've got opportunities there. Sometimes we've got a lot of air leakage and things like that, that technologies like this can be helpful for. It's another question on how much different on new installs with the upfront cost of the ceilings versus normal cost of standard ceilings. Once again, that video might have taken you through that, but just ballparking sort of roughly $2 a square foot is a good walking around number. All of this sort of differs depending on where people are in the country, what their project is, who the contractors are, and things like that. But if you imagine having a project that's maybe $8 or $10 a square foot total, and you add $2 to that, but now you got a 40 to 50% tax credit, your net at the end of that can be quite significantly less than it would have been without adding the thermal mass to the space. And really where we're trying to go with some of this in terms of the energy modeling is trying to better understand opportunities for other things we can do to perhaps optimize, downsize, right-size HVAC equipment, other things that can be done on the cost side of things in the design process. You're happy to speak to that too if you got thoughts around that as well, Nathan.
Yeah, a couple of things that I'd like to pick up on there is also just the notion around thermal comfort. And I think, there's the temperature in the space, which is what you guys were monitoring in that Palm Springs example. But another factor that's really significant in thermal comfort is the surface temperatures. So the radiant heat that's traveling to our bodies constantly and leaving our bodies constantly is also another factor in that comfort. And that definitely, with the phase change material having the properties between roughly 70 and 77 degrees, that means that surface temperature is going to be a lot more comfortable to sense as well. And yes, the integration that we've done with phase change in this context is still using good fundamentals for sizing equipment and doing the calculations, the engineering calculations that would normally be done. So it's a differentiator because a lot of the other methods that are out there that have been published in research, for example, do not use those same methods. So in addition to being more complicated to get your arms around, they also are not necessarily translatable for identifying those types of opportunities. So yes, just kind of trying not to get too nerdy here, but there are a lot of opportunities in that space as well.
One other important point to the reason that Armstrong created the partnership we did with IES is a lot of the feedback we get from energy modeling professionals, even though some of us on the call don't necessarily engage with energy modelers every day of the week. A lot of their work is around code compliance, energy code compliance, and balancing things on tenant improvements and retrofits and renovations. And IES is a tool that's often used to demonstrate some of those code compliances. If you're in California, you know about Title 24 and things like that. And so a lot of the work being done now is advancing in well, how can we use these ceilings to help with, for example, meeting Title 24 compliance? Can I do this instead of having to do a major roof upgrade or, a major window, a very capital intensive project that could potentially get me over the line just by doing thermal mass in my ceilings and filling a gap that often isn't filled with other technologies. You can add more insulation, just kind of thinking about the ice in the cooler. The example I often give to people is you could go camping with a Yeti cooler and put your drinks and food in the Yeti cooler. But if you got no phase change material, it's great to have a really good envelope, but if you don't have phase change material, it would actually probably be better to just go out and get a foam cooler with phase change material, and it's going to perform just as, if not better. And so that's that balance, and it's that thermal mass that's playing that role. It can be really important in a lot of different situations. So we're pretty much at time now, and it doesn't seem to be like there's a lot of extra questions. So, we certainly appreciate everybody's attendance today. And Jack, this might be a good opportunity for us to hand it back to you to help wrap us up. So.
All right. Well, thank you so much for everyone for joining. All registrants will receive a follow-up email with the slide deck and any other resources that are necessary. But thank you so much, and have a great rest of your day. Kim, do you want to have any closing thoughts?
No, I just thought I'd pop in. This was an incredible discussion, a lot of just fact-based information, and I thank you so much for partnering with IFMA and for sharing this knowledge with the facilities teams that are faced with a lot of challenges these days. So thank you so much. And everybody, if you do have questions, feel free to reach out. We'll send a follow-up. Otherwise, have a fantastic day. Thank you.
Thank you.